All right, I guess we're good to go. Can everybody hear me okay? After last time, I want to check. Great. So it's kind of a long unit, kind of a short homework. Not very many questions asked on it, but the questions that are asked are not easy because relativity itself isn't easy. This class is going to stretch your credulity. And yet I swear to you, pretty much everything I'm about to try to teach you is real. The universe really is this strange. It really does work this way. Okay, let's dive into it. Special relativity. Element of the day is technetium. Technetium is interesting in that it's a naturally radioactive element that is in the middle of the periodic table of elements. So it's pretty easy to build. You can just take something nearby it, throw neutrons at it, wait until some of the neutrons turn to protons, and then you have made yourself some technetium. And technetium is valuable because it is radioactive, and it's something we can make that's radioactive that's relatively easy to make. So the way that doctors use technetium is they have you drink it. Now, it doesn't sound like a great idea to swallow something that's radioactive, but once you do swallow it, it goes to your body and emits gamma rays. And the doctors just analyze where the gamma rays are coming from inside of your body to get a great map of your insides. So if you've got a hole in your stomach, the technetium is going to leak out of that hole, and all of a sudden you'll get gamma rays coming from a part of your body where they really shouldn't be. And the doctors know, bingo, that's where the hole is. So there's your element of the day. Not a naturally occurring element, it's too radioactive. I mean, supernovas make technetium, but it falls apart way before it could be absorbed into a newly forming solar system. All right, relativity and black holes. So looked at two different ways stars can die. You can get a white dwarf, it's a little star. You get a neutron star, it's a much bigger star. There is one other way that a star can perish, and that is by making a black hole. So let's start talking special relativity. So you got an astronaut on top of a space station, on top of a spaceship. The ship is moving at 200 miles per hour. The astronaut throws the ball at another astronaut at 50 miles per hour. What speed should the floating astronaut measure the ball? Well, the obvious answer is 250 miles per hour. Sure. Now, consider a slightly different situation. The astronaut on the shuttle is shining a laser at the other astronaut. The laser speed the other astronaut should have observed seems like it should be 300 million meters per second plus 200 miles per hour. But it's not. It literally is just 300 meters per second, even though the astronaut on top of the spaceship is moving. This is actually something really deep. Every observer measures the speed of light as being the same. That means, let's imagine a really beefy spaceship, one that goes at 99% of the speed of light. And then I shine a laser from that spaceship. I do not measure the velocity of that laser beam as being 1.99 times the speed of light. I measure it as being the speed of light, because all observers see the speed of light as being the same thing. That requires a modification to the way the universe works. And the way that the universe keeps the speed of light the same for all observers is that rather than letting the speed of light vary, it will preferentially warp the fabric of space-time in order to keep the speed of light a constant. Why does the universe do this? I don't know. I didn't design it, but it does it. When objects are traveling close to the speed of light, we say they're traveling at relativistic speeds. So even if the shuttle is moving at 50% of the speed of light, and shine a laser light at the speed of light, the other astronaut's going to see that laser as having exactly the same velocity that the person sitting on the spaceship sees it as having. That requires the space in between the two of them to become warped. And that's what special relativity is about. It's the warping of space and time in order to preserve the constancy of the speed of light for every observer. The more extreme the speeds are involved, the more space-time itself warps. So here's a guy who came up with this. His name is Albert Einstein. He's kind of a genius. He invented a lot of things, but special relativity is one of the first things that he did invent. And he developed and published a theory called the theory of special relativity, which correctly describes how objects behave when traveling near the speed of light. Let's go through a thought experiment. You got a train, and the train has a very simple clock on it. What the clock does is the light goes up out of the box, it hits the mirror, and it bounces back. That's one tick of the clock. So up, down, 1 unit of time. Now let's think about that train from the point of view of it moving. So for an observer that is seeing the train move, the clock is covering a different distance. That would mean that the amount of time measured by the observer as being one tick of this clock would be different, excepting that space-time itself warps in such a way as to preserve the constant speed of light. The train is moving slower from the perspective of the person looking in from the outside. And when I say the train is moving slower, I don't mean its velocity is slower. I mean the flow of time on the train is moving slower for the person standing on the outside looking in. To further increase the weirdness, for a person on the train looking out, they also see the flow of time as being slower for the outside world. One of the things that's a tautology of special relativity is that there's no one special reference frame. Every reference frame is equally special. And anytime you have a velocity difference in between the reference frames, time and space distort by similar amounts for both the person inside the reference frame looking out, like a person sitting in a train looking out, and the person outside the reference frame looking in, like a person sitting on a bench watching the train go past. They both observe a time change in the outside world. The person on the train would say that the person sitting on the bench has a heart that is beating slower. The person sitting on the bench would see the person on the train as having a heart that is beating slower. Weird, huh? So time is not an absolute quantity. It is measured differently by observers in different reference frames. Thus, to accurately describe an event, you need 4 quantities, 3 dimensions of space and 1 dimension of time. This 4-dimensional coordinate system is called spacetime. Out of this theory, through some very convoluted math, Einstein knocked out the idea that E equals mc squared, that you can create energy by destroying matter. This is what powers the sun. So that was a lot of confusing words. Let me offer you explanations that are equally confusing, but involve slightly different words. Because as many times as you can hear about this, it always helps to get a different perspective.
When I was young, I was fascinated by elevators. When you went up, everything else seemed to go down. When you go down, the world goes up. When I got older, I got used to the notion that the world isn't really going up or down, but that the only one that was moving was me. Yet, it is somewhat a mistake to ignore what we see. The truth is that going forward, for example in a train, does not affect the Earth too much, but the Earth is moving relative to the people inside. That's the basis of relativity. Sounds simple. Someone moving at relative speed to someone else would look to the other one as if he was moving in the opposite direction and in the same speed, and that is complicated as it gets. but something did not fit. You see, the knowledge gained during the last decades of the 19th century gave more than a hint to the possibility that light does not adhere to relativity. Everyone, moving fast or slow, seemed to be having essentially the same speed of light. It seems benign, but look at that. This craft travels at speeds close to the speed of light. What you just saw was two simultaneous lightning strikes at the forefront and back of the craft. Now, you can see the light from both events coming towards the person in the middle as he is moving towards the light from the front, and the light from the back has to chase him. So, you will see the lightning from the front first. So far so good. However, and pay close attention to this, relative to him, the light comes at the same speed and takes the same time to reach him from both directions. So for him, seeing the front lightning strikes before the one in the back means the front strike first. Something is very wrong. Or is it? The greatness of Einstein was that he managed to understand it is possible to reconcile relativity with a notion of unchanging speed of light. He did that by adding something to the theory of relativity: time. Time, he said, is relative. Simultaneity is relative. And that's not all. Let's take a look at the length of the craft. We'll assume we can estimate the distance between the lightnings in the photo. As we've seen earlier, relative to the person inside and the craft, the front meets point A first and the rear meets B a little later. So from inside, length A to B seems to be shorter. This is what's called length contraction. The vector by which the contraction occurs is called the Lorentz vector. The Lorentz vector stays close to 1 for most velocities, but rises fast when approaching the speed of light. In almost the same way, it can be shown that a moving clock will tick slower than a stationary one, and by the same vector. The general rules of relativistic location and time have been summarized by equations called the Lorenz Equations. These equations have some other interesting implications. For example, if someone throws a ball in a moving car, it's reasonable to assume that we can sum that speed and the speed of the car, and that will be the speed of the ball relative to the outside world. The Lorentz equations tell us it will actually be slower, never over the speed of light in vacuum, by the way. But the most famous implication stems from the derived equation for energy. What we get is energy equal to the Lorentz vector multiplied by mass and the speed of light squared. While fast things have a lot of energy, when they are standing still, Lorentz vector of 1, they do have some energy, quite a lot actually. It seems that everything has energy just by having mass. Releasing or capturing energy, by the way, changes the mass. While these predictions of his theory seem weird at best, and are definitely not apparent on our day-to-day experiences, they have been tested innumerable number of times. Clocks really do tick slower at different speeds, lengths do change, and so on. Time is relative, and everything that stems from it is, well, weird, but real.
Okay, so there was his attempt to help you wrap your head around it. Any questions? Let me go back to the key feature of what I think the key feature of that video is. So let's imagine two events. It could be anything. For the sake of simplicity, I'll just say that there are two volcanoes that have erupted. We got Mount Hood and Mount Rainier. I have no idea if they're active, but I do know that those used to be volcanoes at least. if I am not moving relative to these two mountains, I see them erupt at the same time. Easy enough? If I'm moving this way, then I see Mount Rainier erupt before Mount Hood. And if I'm moving the other way, I see Mount Hood erupt before Mount Rainier. And when I say that I see them erupt first, what I mean is that they do erupt first. The order of events changes depending on my velocity. I'm not talking about when I see the light from the eruption or anything like that. I'm saying that Mount Rainier physically does erupt before Mount Hood, or Mount Hood physically does erupt before Mount Rainier. And I can change the order of events just by changing my speed and direction of my travel. So that's true and weird. Now there is a limit to this. You cannot use this to, for example, time travel and go back to before your grandparents were dead. If there's enough time for the light from Mount Hood to reach Mount Rainier, or vice versa, then you can't pull this trick anymore. It just doesn't work. But if there isn't enough time for the light from one event to reach another, then you can absolutely change the order of events by changing your velocity. The higher your velocity, the more offset in time the order of events becomes. So yeah, the universe does that. And it does that, again, because it wants to maintain a constant speed of light. And once you require the universe has the same speed of light for every observer, you're led down this rabbit hole of thinking that leads to conclusions like this. And we've tested these conclusions scientifically. It really does happen at very high speeds, but it really does happen. Now, if that weren't confusing enough,
The theory of special relativity,
here's another point of view for you.
associated with Albert Einstein, has proven to be one of the most successful theories in all of physics, surviving any test you can think of to try to prove it wrong. However, it has a reputation for only being possible to learn through headache-inducing thought experiments where the student has to keep up with pulses of light, multiple clocks, and moving observers, all while trying to adapt to a new concept in space and time. While all of this is fascinating, and I really encourage you to look into the thought experiment development of special relativity, my goal in this video is to present you with a more direct intuition for how special relativity works without using as much math. Let's start with explaining Galilean relativity, where the outcome of any experiment will be the same regardless of the frame of reference. That is to say, if all relevant parts of the experiment are given some boost with the same speed and direction, the experiment will come out the same. The concept of a boost will be important later on. For this discussion, think of a boost as a push to the frame of reference. Imagine throwing a ball straight up in the driveway. It will fall straight down. Now imagine that you and the ball are in a car that is moving at a constant 60 miles per hour west. From the frame of reference of the ground, if you throw the ball up, it will move upward, but also westward at 60 miles per hour to form an arc. If I asked what the ball looks like to you, you would quickly tell me that it looks like it is moving straight up and straight down, just like in your driveway. While this seems obvious, it is only because of symmetry that we can make this assumption. The idea behind Galilean relativity is that you can skip this step where you consider the frame of reference from the ground because of the symmetry between all frames of reference. In fact, the ground is just Earth's surface, which is rotating at some 1,000 miles per hour relative to the axis. But even the axis orbits the sun, which in turn orbits the galaxy. It therefore follows that all frames of reference are equally valid, or in other words, there is no way to determine if you are moving or at rest in any absolute sense. Only the relative motion between different objects is meaningful. This is called the principle of relativity. Okay, now we need to switch gears for a minute to talk a little bit about electromagnetism and waves. Electromagnetism is the theory describing the one unified interaction between charges, currents, magnets, and light. In the 19th century, it was realized that the equations for electromagnetism had a class of solutions that corresponded to physical waves in the electromagnetic field. It did not take long for experiments to produce these electromagnetic waves in the laboratory and confirm that light is just a small subset of these waves with a particular range of frequency.
The electromagnetic field was thought to exist in the ether, with its own state of motion, through which electromagnetic waves of light traveled at relative speed of 300 million meters per second. This, however, poses a problem for Galilean relativity. See why? We are going to use an analogy: water waves. Imagine you are floating in a lake and you drop a baseball in the water. The disturbance created in the height and motion of the water will propagate outward as an expanding ring. This ring will let us determine if we are at rest with respect to the water. As long as you are in this lake, you can determine if you are at rest by dropping a baseball in the water and checking to see if you remain in the center of the expanding ring-shaped wave around you. If you are moving, you will be able to see this as the center of the expanding wave moves away from you. You don't stay in the center of the expanding ring. Giving such a test to determine if you are moving or at rest may seem to contradict the principle of relativity. But remember, you are only measuring your motion relative to the water and its associated frame of reference. So, according to the ether idea, we should be able to do the same thing with an electromagnetic or light wave as we did in the lake, which would mean that we should be able to see our movement in the ether by measuring light waves. Physicists Albert Michelson and Edward Morley tried an experiment to measure this. What they found is that it does not appear that there is any motion at all through the ether, even at times of year when the Earth is moving at a velocity up to 60 kilometers per second to the ring. This experiment showed that the ether theory was wrong, and that the electromagnetic field did not behave like some cosmic wave with a fixed background frame. Instead, the electromagnetic field treats all frames of reference equally, which means that the speed of light is 300 million meters per second in every frame of reference. This is called the principle of constancy of the speed of light. But wait, how can this be consistent with Galilean relativity? Galilean relativity says that if the Galileo Galilei is moving toward you at 1 million meters per second, and he shines a light at you that leaves him at 300 million meters per second, the light will arrive to you moving at 301 million meters per second, breaking the principle of constancy of the speed of light. This inconsistency led theoretical physicists Henri Poincaré, Albert Einstein, Friedrich Lorentz, as well as mathematician Hermann Minkowski to develop a new theory of space and time. Somehow it had to be true that there is no preferred frame of reference, and the speed of light is the same in all frames of reference. Instead of following the original thinking of Einstein or Lorentz, I'm going to use the fact that everyone thinks they are in the center of the universe. No, really, all observers see themselves as staying in the center of a pulse of light emitted from them, regardless of their state of motion. The resolution found by the fathers of special relativity requires replacing Galilean relativity. So we need a symmetry that respects the principle of relativity and also the principle of constancy of the speed of light. Enter Lorentzian relativity, which was discovered by Lorentz and Einstein. A visualization of the principle of relativity will require a geometry in which every point in every direction is essentially the same. There is a theorem in mathematics that there are exactly 3 such geometries. To begin with, let's look at a geometry that does not satisfy this problem. On the cube, not any 2 points are the same. For example, while these 2 points are geometrically equivalent, these 2 are not. The first geometry that does fit our criteria is the plane. Since the plane is infinite, any point can call itself the center. The next one is the sphere. Since the sphere is perfectly round, any point can call itself the center or the pole. In both of these geometries, each point is basically the same. The third and final geometry is one that is less familiar, since there is no perfect way to represent it in 3-dimensional space. It is called the hyperbolic plane, and it is what we will use to understand relativity. In our visualization, the regular plane will represent Galilean relativity, and the hyperbolic plane will represent Lorentzian relativity. So here we go. Imagine a car is moving at some speed through a large parking lot. According to Newtonian physics, the car can have any speed in any direction. The speed of the car can be represented as a point on this grid of tiles. To move from one tile to the adjacent one would require a standard boost, say 10 miles per hour. Remember that a boost is just a push into the new frame of reference. Each point on this circle represents a velocity of 10 miles per hour in a different direction, and each point on this circle represents a velocity of 20 miles per hour. This grid represents Galilean relativity. Notice that no particular tile is special. We can easily shift the grid around and put any tile in the center. Now I am going to state something that will become clear later. Nothing can move faster than the speed of light. Therefore, the velocities that the car can move at are represented inside this circle. For example, this point represents half the speed of light north. If you imagine that this circle is the size of a dinner plate, any speed that would practically be obtained by a vehicle on Earth stay in a tiny circle only about 1,000 atoms in diameter. So the new grid of tiles looks like this. The most important thing to understand is that the tiles become more and more compressed near the boundary. Each tile is still the same amount of boost, but they shrink in size as you approach the edge. This explains why you can never get to the speed of light. To increase your speed, you need to undergo a certain boost, moving to the next tile. But as you get near the speed of light, each tile takes you less and less distance with the same boost. So while the speed of light is only a finite number of meters per second away, it is still an infinite number of tiles that you must cross to get there. So you can see that when you compare our two grids, that in the first one, which represents Galilean relativity, the velocities are added. Each tile adds the same amount of boost or change in velocity regardless of which frame of reference you are observing it from. In the second grid, which represents Lorentzian relativity, each tile adds the same amount of boost, but it looks completely different depending on where you are viewing it from. If you are viewing a change that is far away, the boost per tile appears very small, but if you are in the center or close by, the tile appears very large. With a bit of visualization, you can imagine that the grid can be shifted so that this arc moves to this arc, with all of these tiles getting compressed over here, and these tiles expanding to fill up all of this space. So you can see that any tile could reasonably call itself the center tile, and so it follows each tile sees the speed of light as a circle around it. Now maybe you can see why, with Lorentzian relativity, each observer sees light emitted from them moving out in a perfect sphere regardless of their state of motion, which in our visualization is represented by which tile they are on. One last thing to note is that Galilean relativity is an approximation to Lorentzian relativity, as long as the speeds involved are small. For example, the 1,000 atom diameter circle representing typical speeds of cubic vehicles is hardly affected by the distorting near the speed of light. The theory of special relativity found by Einstein gave rise to a whole new picture of space and time, which became incorporated into some of the most profound and successful theories in all of physics. I wish I could go on to talk about these ideas of space-time and mass energy, but unfortunately, I'm out of time. I hope I've given you a taste of special relativity and why you can never reach the speed of light without using all of this. I want to encourage anyone interested to find material on the topic of special relativity and to look at the woodcut Circle Limit 3 by M.C. Escher, which inspired this video.
Okay. Any questions come up thus far about the extremely confusing topic of special relativity? Well, let's dive deeper then. Nope, no chats? All right. You all know the drill. Hit period enter if you have a question you want to ask. So objects with mass can never quite reach the speed of light, even if they keep accelerating forever. Only light and other massless particles can actually travel at that speed, and that's the only speed it travels at. So we see examples of this in all kinds of different ways. For example, stuff is flying in towards Earth's atmosphere all the time. It hits some particle up in the upper atmosphere and that blows the particle to pieces. And then we have these very short-lived daughter particles that come cascading down towards the Earth. Now we know that these things exist for such a short period of time that they should never reach the surface of the Earth, but they do. And the reason behind why is special relativity. From the point of view of the particle, the Earth's surface is much closer than it would be as if we measured it standing still and looking up. And from our point of view, the particle itself is being time dilated such that its lifetime is many times longer than it would be if it were at rest. Time dilation and length contraction, two inevitable consequences of the constancy of the speed of light. So from muon's perspective, the ground looks much closer. From our perspective, the muon's internal clock is running slow. Suppose you're on Earth and your friend flies past you in a spaceship. Both of you measure the times it would take for the spaceship to fly by your location. Which of the following is true? Would you measure time as being longer than what your friend measures? Would the time that you measure be shorter than what your friend measures, or would you both measure the same amount of time? I'll let you think about it for about 20 seconds. Come up with an answer, which you don't have to share in chat. And the actual correct answer is A. The time you measure is longer than the time your friend measures. Now, why would this be? Think about it. Time dilation and length contraction. Let's do another one. Suppose you're on Earth and a friend flies past you in a spaceship. Both of you measure the time it takes a spaceship to pass by your location. Which of the following is true? Does the distance between the Earth and the space shuttle, is it further according to you? Is the distance between the Earth and the space shuttle further according to your friend, or you both measure the same distance? The distance between the Earth and the space shuttle is further according to you. If we ever do get space travel locked down, this is one of the ways it will work. The faster you get moving, the shorter distances become. Weird, but true. One of the most common illustrations of special relativity is something called the pole and barn, or the train and tunnel paradox. It's the same thing. And it's a really famous thought experiment. No actual macroscopic object could be big enough to go through these kinds of situations. But just for the sake of the analogy, let's pretend.
According to Einstein's theory of relativity, Sarah will see the length of this train as shorter due to the fact that from her perspective, the train is moving at close to the speed of light. From Sarah's point of view, the train has shrunk, and the train is shorter than the tunnel. From Adam's perspective, the train is standing still, and it is the rest of the Earth which is moving in the opposite direction. Therefore, from Adam's perspective, the train is still at its normal length, and it is the length of the rest of the Earth which has become shorter. According to Einstein's theory of relativity, both points of view are equally valid. Suppose that this train passes through a tunnel. Suppose that while the train is inside the tunnel, we briefly close the doors at the entrance and exit of the tunnel. From Sarah's point of view, the train has shrunk, and the train is shorter than the tunnel. From Adam's point of view, the tunnel has shrunk, and the tunnel is shorter than the train. Although Adam and Sarah can disagree about whether it is the tunnel or the train that is shrunk, they must agree on whether or not the doors hit the train when they tried to close. So, if Sarah sees that the doors did not hit the train when they closed, Adam must also see that the doors did not hit the train. But how is this possible when Adam sees the tunnel as being shorter than the train? The answer is that according to Einstein's theory of relativity, different observers can disagree about whether or not two events happened at the same time. From Sarah's point of view, the doors at the entrance and the exit of the tunnel closed at the same time. From Adam's point of view, the doors did not close at the same time. Therefore, Adam will see that the train passed through the tunnel without being hit by the doors, even though from his perspective, the tunnel is shorter than the train. Now let us consider a different scenario. This time, the doors close and never reopen, thereby permanently trapping the train inside the tunnel. Since Sarah sees the full length of the train completely trapped inside the tunnel, Adam must therefore see the same thing. But how is this possible? The answer lies in the fact that the train is not a rigid body. That is, it cannot be thought of as a single solid rectangle. Instead, we need to think of it as many separate rectangles that are tied together through flexible connections. If the train were a single solid rectangle, then when we applied a force on one side of the train, the force would be immediately felt on the other side of the train. However, this would mean that we sent a signal instantaneously from one side of the rectangle to the other, which would violate Einstein's principle that no information can travel faster than the speed of light. On the other hand, if we think of the train as many separate rectangles, then when we apply a force to one side of the train, the other side of the rectangle will not know about it until much later, and hence the signal has not traveled faster than the speed of light. If we assume that the doors to the tunnel are unbreakable, then when the train hits the closed door at the tunnel's exit, the front of the train will stop first, while the back of the train will initially keep moving at the same speed as before, and stop much later.
A bad situation for Adam, to be sure. So that is one of the two famous paradoxes of special relativity. And you see how it brings together some stuff that we talked about before. The order of events can change with a certain amount of velocity. For Adam, the two doors are not closed at the same time. For Sarah, they are. They have a different reference frame, and that makes the difference in when the events occur. Now there is another super famous paradox called the twin paradox. Let me introduce you to it real quick. So imagine you take a trip into deep space in a space shuttle traveling close to the speed of light. Your twin remains behind on Earth. Which one of you is older after you return? This is a real tricky one because I said the time dilation goes both ways. Like the person on the spaceship looks backwards and they see their twin's heart is beating slower. The person on Earth looks at the spaceship and they see their twin's heart is beating slower. This is a problem that cannot be solved just with special relativity. It takes a wee bit of general relativity too. But the answer is that the twin on Earth will be older. And it's really true. Let's look at why. Start at 2 minutes, 40 seconds.
I cracked the code to lighting. Hi, I'm Joel Grimes. I'm a commercial.
Gravitational field present that is canceling out the
So,
each of them will think that the other person's clock is moving slower than their own.
so what creates the difference? This difference is created because the twin that returns, the twin that's on the spaceship, has to accelerate. When they accelerate, they're experiencing a velocity that is not constant. This is no longer the realm of special relativity, it's become the realm of general relativity that governs how gravity and how acceleration work the structure of space-time. Because this twin is going through an acceleration.
That the spaceship is standing still, he needs to also believe that there is now a gravitational field present that is canceling out the force from his rockets. Adam will believe that this gravitational field exists everywhere throughout all of space, and that this gravitational field is causing the Earth and the rest of the universe to accelerate towards him. Gravity affects the flow of time. Suppose we are in a region of space where the strength of the gravitational field is the same everywhere. The amount by which one clock will flow faster than another will depend on how far apart the two clocks are along the direction of this field.
And when Adam turns around and accelerates, he is very far away from the Earth, which explains the huge time difference between his age and his twin's age. Like I said, I swear to you guys, it's all real, but I would not blame you if you didn't believe me. Was there a question? Nope. All right. Back to the slides then. Long slides. Right slides. So this is general relativity. 10 years after Einstein published his theory of special relativity, he expanded to include general relativity, which gives a modern explanation of how gravity works. Gravity warps space-time the same way that space-time can be warped by objects moving very close to the speed of light. General relativity explains gravity in all situations. Newton's laws of gravity are a subset of general relativity that work well for slow-moving systems like planets and stars. Special relativity tells us there's no way to distinguish a stationary reference frame and a reference frame moving at constant velocity. General relativity adds that a reference frame in gravitational freefall is indistinguishable from the reference frames above. So you can't tell whether you are in freefall or whether there's just no gravity. There's no experiment you can do that could detect it. Space-time itself curves, and mass can warp the curvature of space-time. The more mass you have, the more warped space-time gets. This has all kinds of cool effects, like, for example, light travels in a straight line, but if space-time is warped, then light will dip down into the valley and emerge in a different direction. The shortest path between 2 points is not always a straight line. The Earth is a curved sphere, for example. That's why airplanes take curved flight paths. The more massive an object, the more heavily it distorts space-time. So a low-mass star would distort it by a certain amount. A high-mass neutron star would distort it by a lot more. Orbits are really circular or elliptical geodesics. They're simply a natural path that an object will follow in curved space-time. In other words, you can think of the sun as being a big bowling ball in the center of the solar system, and the planets as being little marbles rolling around in the dent that the bowling ball creates. One of the big consequences of general relativity is gravitational lensing. When light goes by a really massive object, it can change directions. For example, the sun changes the path of light that travels near it by a very small amount. A neutron star would change it by more. This effectively makes it so the stars are seen as being in different positions relative to where we see them when their light is passing by the sun than where we see them when the light is going nowhere near the sun. And that was exactly Einstein's experiment to prove general relativity. He had people take pictures of stars in a certain part of the sky, waited for a solar eclipse, because otherwise you can't see the stars near the sun, and then took the exact same pictures. And indeed, the stars were a little bit offset from each other. Proof of general relativity. Another pretty picture of gravitational lensing. If there's a truly massive object, like a big old galaxy cluster, then sometimes we see many, many, many different images of the same object because the light is able to take several different paths around that massive structure in between, and it gets curved so that it comes to us from a couple of different perspectives. Every once in a while, the light makes a complete journey around a gravity cluster, and instead of seeing one or two images of the object, we see an entire ring called an Einstein ring. And then just to show you what this looks like in live action. There we go. That's gravitational lensing. Boom. And again, it is a real effect. We've confirmed it in many different ways using many different experimental lines of evidence. I'm going to skip this and go on to gravitational red shifting. So the speed of light is a constant. It's always moving at the speed of light, but that doesn't mean that nothing changes when light has to escape the gravitational well. It takes energy for light to get away from a really massive object, and it can't travel any slower, so its wavelength gets longer. Its color gets redder. That's called gravitational red shifting. So, for example, light that's leaving the surface of a neutron star as blue light would be red light by the time it finally emerges. So normal stars don't do much gravitational red shifting. White dwarfs would do some, and neutron stars would do quite a bit. Time does run slower, deeper in a gravitational field. We physically dug holes in the Earth and buried clocks there to confirm that. In order for GPS satellites to accurately tell you your location and speed, the clocks must be perfectly synced with the clocks on your Earth. So GPS satellites have to take into account both general relativity, because they aren't in the same gravitational field that we are, and special relativity, because they're orbiting around the Earth at a pretty high rate of speed. If they didn't take account of that, special relativity would make the GPS clocks run slower by 5 microseconds per day, and general relativity would make the GPS clocks run faster by 45 microseconds every day. And that sort of thing would add up. Another evidence for general relativity is that we have now found gravitational waves. So the fabric of space-time is something like a tarp. Then objects that are moving around the tarp should generate waves, like kids running around on a trampoline. And this is the device that detects it. It's called LIGO, Laser Interference Gravitational Wave Observatory, and it's just shooting lasers back and forth. And the lasers interfere with each other, and anytime there's any difference in the interference pattern, we say, oh, could a gravitational wave have just passed through? And now we're pretty sure that that is what is happening, because we co-located both the interference pattern shifting and waves from supernovas that have reached us. So clearly they are gravitational waves because there's something massive that just happened that's causing them. I think I'm going to skip these videos. You can watch them if you like. And finally, we come to black holes, the last topic in this unit. How do you make a black hole? There's really only a couple of different ways. First off, you can be the very biggest star that exists, and then you could explode. And when that happens, the star goes through the process that would make a neutron star, but the neutron degeneracy pressure is not strong enough to fight gravity. So instead of the star being entirely limited to being the density of a nucleus, the star itself shrinks until it occupies no space at all. And another way you can make a black hole is you can have a couple of neutron stars that collide with each other. And that has enough mass to create a black hole. And those are the only two ways.
Every day or two, on average, satellites detect a massive explosion somewhere in the sky. These are gamma ray bursts, the brightest blasts in the universe. They're thought to be caused by jets of matter moving near the speed of light associated with the births of black holes. Gamma ray bursts that last longer than 2 seconds are the most common and are thought to result from the death of a massive star. Shorter bursts prove much more elusive. In fact, even some of their basic properties were unknown until NASA's SWIFT satellite began work in 2004. Astronomers suspected that crashing neutron stars could explain short bursts. A neutron star is what remains when a star several times the mass of the sun collapses and explodes. With more than the sun's mass packed into a sphere less than 18 miles across, these objects are incredibly dense. Just the sugar cube-sized piece of neutron star can weigh as much as all the water in the Great Lakes. When two orbiting neutron stars collide, they merge and form a black hole, releasing enormous amounts of energy in the process. Armed with state-of-the-art supercomputer models, scientists have shown that colliding neutron stars can produce the energetic jet required for a gamma ray burst. Earlier simulations demonstrated that mergers can make black holes. Others had shown that the high-speed particle jets needed to make a gamma ray burst would continue if placed in the swirling wreckage of a recent merger. Now, the simulations reveal the middle step of the process, how the merging star's magnetic field organizes itself into outwardly directed components capable of forming a jet. The Damiana supercomputer at Germany's Max Planck Institute for Gravitational Physics needed 6 weeks to reveal the details of a process that unfolds in just 35 thousandths of a second. The new simulation shows two neutron stars merging to form a black hole surrounded by superhot plasma. On the left is a map of the density of the stars as they scramble their matter into a dense hot cloud of swirling debris. On the right is a map of the magnetic fields, with blue representing magnetic strength a billion times greater than the sun's. The simulation shows the same disorderly behavior of the matter and magnetic fields. Both structures gradually become more organized, but what's important here is the white magnetic field. Amidst this incredible turmoil, the white field has taken on the character of a jet, although no matter is flowing through it when the simulation ends. Showing that chaotic magnetic fields suddenly become organized as jets provides scientists with the missing link. It confirms that merging neutron stars can indeed produce short gamma-ray bursts. At this moment, somewhere across the cosmos, it's about to happen again.
So these are so bright that when we say we see one a day, we mean we're seeing one a day in other galaxies. As I said, there is a star near enough to us that it will undergo a gamma ray burst. But Eta Carinae's poles are not pointed towards us, so it's not inevitably going to kill us. When a really big star goes supernova and leaves behind a black hole, we call it a hypernova. And a characteristic of the hypernova is they make these forms of jets. These are the long duration gamma ray bursters. So there's the iron core, shrinks in the process of forming a neutron star, and it makes those jets to the top and the bottom of the star. Not every supernova makes jets like this, but hypernovas do. And you do not want to be in the way of them. So we can predict when hypernovas are going to happen if we can see the stars that are going to create them. But nobody knows when neutron stars are going to collide. And I can unfortunately offer you no surety that we are safe from that. For all we know, there could be a neutron star, a couple of neutron stars orbiting each other, getting a little closer every single year, just waiting to go off. General relativity also predicts the existence of black holes. So you got a normal star like the sun, deforms space-time by a little bit. White dwarfs, which have their electron shells touching, so they're held up by what's called electron degeneracy pressure. The electrons don't want to pass each other. Neutron stars, where the electron shells have shattered, that are held up by neutron degeneracy pressure. So they're about as dense as the center of an atom, only it's, you know, a city-sized thing. But black holes are what happens when neutron degeneracy pressure can't fight gravity anymore. In that case, all of the mass goes straight to the center. And as far as our math goes, space-time basically seems to rip. If you could see a black hole, it'd look like this. They're black. The gravity of a black hole is so large that in order to leave the surface of a black hole, you would have to be going faster than the speed of light. Nothing goes faster than the speed of light, hence black holes are invisible. And there is a certain distance at which you could approach one where you would never make it back out. The event horizon is the point of no return, the point at which the escape velocity equals the speed of light. The matter in the black hole isn't there, it's right at the very center. If you were to pass the point of no return, you wouldn't necessarily notice that anything was going wrong, excepting, of course, that the gravitational forces on you would be quite huge, and that would cause a host of problems. If the sun were to collapse into a black hole, which it won't, its event horizon would be 3 kilometers wide, much smaller than San Francisco. And all the matter in the sun wouldn't be at that 3 kilometers distance, it would be in an infinitesimally small spot right in the center. Now, here's what would happen to you if you fell into a black hole. The tidal force of the black hole would exert a lot more force on your feet than on your head. It would start to pull your body out into a string. This is called spaghettification. It's literally what we call it. Pretty easy word to remember since it describes the process of being turned into spaghetti. If you were on the outside watching somebody fall into a black hole, the person would become redder and redder and redder as gravitational red shifting takes more and more energy of the photons that are reflecting off of their body. And you would become redder as you get closer to the black hole, and then you'd finally slowly start to fade away. Time would appear to stop for you at the event horizon, and you would just get dimmer and dimmer and dimmer. Weird, but true. Assuming the astronaut's eyeballs aren't ripped apart, he would see the rest of the universe speeding up as they got closer to the black hole. The event horizon would not be any kind of special place. It would just mark the location from which they could no longer be able to turn around. Suppose you're standing on a normal star with a flashlight and you shine the flashlight straight up. Most of those photons are just going to go straight. But if you were near an object with a lot more mass that's curving space-time much, much, much more, then you would have to have the perfect trajectory to actually have the light get away. All the rest of the photons would curve around and end up rejoining the object, rejoining the black hole, or the star, or the neutron star, or whatever. When an object passes the event horizon, we had no way to measure it, but there are three quantities that you can measure about a black hole. Mass. The more massive a black hole is, the bigger its event horizon is. You can measure how fast it's spinning, because the black hole itself is physically dragging space-time with it as it spins. You can measure how much space-time is being dragged by. And charge. You know, there's equal amounts of positive and negative charges in the universe, so it's hard to imagine how a black hole would develop a net charge, but it could have one in theory. And if we tossed a bunch of electrons into a black hole, then in principle, we could then create electric fields and steer the black hole around without touching it at all. We can't see them directly, but we infer their existence in a lot of different ways. For one thing, some black holes are really massive. For example, the black hole at the center of this galaxy is huge. And there's lots of stars that are orbiting right around it. And so you just figure out where the center of the mass of where the stars are orbiting around, and voila, you found the black hole. Also, black holes will rip apart any object that comes too near to them. So when they do that, they make jets to the top and the bottom, and those jets shine in X-ray light. More examples of black holes eating stars. And there's another final possible theoretical way to see a black hole. And this is what Stephen Hawking is famous for. Bear with me. This is the last weird thing I'm going to talk about before this class is over. The universe is constantly creating particle-antiparticle pairs. It's just something it does. It doesn't really matter because they're always being made in pairs, and they self-annihilate soon after their creation. So nothing, bloop, into existence, bloop, out of existence. We know the universe does this for sure. Now, the next part of this is more speculative. Suppose that the universe does this near a black hole. Let's say my nose is the event horizon. Bloop. This particle is behind the event horizon. It's never getting out. This particle is probably also going to get eaten by the black hole. But every once in a blue moon, it might not. It might have just the perfect trajectory to escape. If it has that trajectory and it gets free out in the universe, then physics suggests the black hole is on the hook to give up the matter necessary to make it exist. This is called black hole evaporation. And in theory, every black hole will eventually evaporate due to this particle-antiparticle interaction. The universe is constantly doing this, bloop, and this particle can be behind the event horizon, not escaping for sure. And every once in a while, this particle gets away, And the mass of the black hole goes down by the amount of 1 electron, or whatever the particle was. It's a very slow way to cease to exist. And the more massive a black hole is, the slower the process works, because massive black holes have tons of gravity to recapture those errant particles. But yeah, in theory, every black hole is a stream of particles coming from right outside the event horizon. And those particles are called Hawking radiation. Only the very smallest black holes would have had time to evaporate in the age of the universe. The supermassive black holes are going to take much, much, much longer. But the universe is inexorable. It will eventually happen. All the black holes will eventually evaporate. And that's it. I'm going to let you peruse the Planet of the Day stuff for Uranus on your own. And I am going to get home because it is cold and I'm wearing shorts. I didn't really think ahead. So on Tuesday, I'll log in and I'll teach lesson 13, lesson 14, lesson 15, and I'll record all those sessions. Anybody got any questions for me before I go?
Professor, how do black holes not gain mass from all of the objects they're pulling in?
Well, generally they do gain mass. Like a black hole will hungrily eat until everything in its environment is gone. So if the black hole is acquiring new mass, like if the black hole has a companion star, it's going to rip that star apart and it's going to get to be more massive by the amount of one star. However, eventually you run out of stuff to consume. Like black holes will slowly clear out their cosmic neighborhood. And after that time has passed, that's when black hole evaporation can, in theory, start to make them slowly be less massive. In theory. Out of all the things that I've talked about today, Hawking radiation is the most controversial. It probably exists, but it's very hard to prove that it exists. We don't have any black holes we can go out to study. And the amount of particles that are created through Hawking radiation is so few that it's not like we can infer their existence without having a ship right next to it taking observations. Anybody else got any questions?
Yeah, I was wondering if there was another secret code for this
Oh,
class.
I didn't give you another secret code, of course. Well, I guess the secret code is right at the very end. The secret code is the rain in Spain stays mainly on the plane. So the rain in Spain stays mainly on the plane. There you go. Just write that at the top of your Unit 14 homework, and I will figure out a way for you to get it to me, and that will be great. And you guys will get extra credit. And I appreciate your dropping by and being interested in learning the rest of the material in the class. I imagine that most of you are probably here for the extra credit, but I hope that you found these classes to at least be interesting. I'm never going to teach anything as weird as special relativity, because special relativity is the weirdest thing in the universe as far as I'm concerned. So hope you had fun with it. If you don't believe in it, that's fine. Some days I'm not so sure I believe it. Okay.